see, let me know. Hopefully it's fine.
You should stop long.
Okay, because I was standing right there, Garrett, will you tell everybody what an isotope is?
It's like an atom that has, like, it's the amount of protons is the same, but it's a different amount of neutrons, so it changes the mass for the...
Very well said. Have a smiley face for that. Great, so isotopes are this idea of when I look at the periodic table, the only thing I can guarantee from the periodic table is the proton. You can't guarantee neutron, you can't guarantee electrons, because if it's charged, that changes electrons, and then there's the range of isotopes that it could be. Now it does all connect to this red number, because the red number, how does that connect to isotopes?
It's lead.
Lily?
Isn't it like the weighted average of the isotopes?
Yeah, so if you do that calculation we did of the weighted average, that's how we get this. So the isotopes should be within a range of that number, but there's no set like plus or minus, but that's where they come from. Yeah.
What are the numbers with the parentheses?
Great question and great observation too, Bryson. So these ones, and you'll notice it's mostly the man-made ones and the bigger ones. It's because they've only made one isotope of it. And so you can't have an average if there's only one. They're also, even the ones that haven't been created, they're also very unstable, so they don't exist for very long. And so like we haven't found other isotopes that exist of them right now. So yeah, good observation. So what we're going to first talk about today, we got two parts of our lesson. The first part is kind of balancing off from last time, and then we'll move on to how we deal with atoms, because atoms are way too small to actually like use, but how do we connect to them? So this idea of isotopes, there's actually an experimental device, I think I mentioned to it last time, but it's known as a mass spectrometer. We don't have one here at the school because they're quite pricey. But I should pull a picture, but literally it just looks like a box from the outside. You don't see any of the compartments unless you break it apart, but it just looks like a box. But the idea of a mass spectrometer is they can do a lot of really cool things. They can help you determine molecular mass. They can help you identify unknown. Actually, this is not what I want. Does this look different than yours?
That looks different.
This is different. Sorry, wrong class. Back up here.
Oh, that's not Wait, so you're not what? You can't stop. You just in a good way. Yeah.
Okay, that looks better. Okay, so the idea is a mass spectrometer can take a substance and it breaks it down. If it's a pure substance, so let's say if it's just carbon, it can break down carbon into individual atoms and then sort them by their mass. It actually can get even more complicated if it's like a whole compound with like lots of different things in it, like dopamine, right? Dopamine has carbon, oxygen, hydrogen, nitrogen. It can break it down into very small pieces and you can identify things from it. That's way more complicated than we're going to do in this class. But it's actually used to identify unknowns, right? If you go to a crime scene and find a white powder, you're like, I wonder what this white powder can be. You don't test it by mouth, because that's not a safe thing to do. But you can throw it to a mass spectrometer and be like, oh, it's just powdered sugar, it's not cocaine, right? Like you can identify that, okay? In our case, we're just focused on it from the isotope standpoint, okay? Now, here's my simple analogy. It's quite complicated, but hopefully this at least gives you a basic idea of how the machine works. Doesn't really matter if you like really know how it works, we just need to know how to interpret the graphs from it. But for example, where did my little things go? Okay, so I have two balls here, okay, a very light but large one and a small marble, okay? So if I had, I was gonna bring it, I forgot. If I had a blow dryer, okay, and I turned on my blow dryer so it's blowing a constant stream of air, okay, imagine this with me, okay, and then I roll the marble in front of the blow dryer and then I roll this one in front of the blow dryer, are they gonna be affected the same?
No.
Why not?
Bigger.
Yeah, their size and their mass are going to influence how much they get deflected,
Yes.
right? That's in a sense how a mass spectrometer works. It's not using air, though, it's using a magnetic field. But the idea is the same, is that something that is very large isn't going to get deflected a whole lot because it's heavier. Something that's very small will get deflected a lot, and then that's how they get sorted, okay? So we'll kind of look at a graph here of what it looks like. So in the end, this is what a mass spec graph looks like as they then hit the detector at the end. So imagine the balls roll to the end and then they hit a screen, and all the ones of the same mass are going to hit the same spot, and that's what will increase the height of the graph, right? This represents how many balls hit there versus here and there. Bryson.
Now, like, how would they get the samples to measure them? Like, for like maybe like example carbon, would they like get pure carbon, or like would they just like take an air sample and just put it in?
If you're doing it for isotope purposes, you do pure carbon, because otherwise you get like tons of peaks for everything that's in there. That's why these can get quite complicated for compounds, but you can actually then still break down the data of what it is. Yeah, great question.
Can pure carbon be like all just one isotope, or is it normally like a lot of different isotopes?
Great question too, Jack. So yeah, there's a law in chemistry, which by the way, like a law is like a foundational truth. It's not just like if the laws don't exist, our world falls apart as we know it, because right, like the law of mass and things like that. So there's actually a law called the law of definite proportions, where scientists have found that no matter where you gather a sample from, the proportion of the isotopes is always the same. So no matter what, your graph for carbon would look the same regardless of where you gathered it, which is crazy. Even if you get a big scoop or a little scoop, it's always going to have the same distribution every time. At least every time they've tested it, it's never been found to be false. So yeah, kind of interesting. Yeah, Lily?
So then there's not like areas that there is a very like one isotope heavy sample of carbon?
Not naturally, right? Like us as chemists, you can make something called heavy water, which has like heavier isotopes of it, but it's not like, as far as it's not naturally found to be that way. So yeah. So as we look at this graph, obviously with any graph we look at, pay attention to the axes, right? What is the y-axis telling us? What is the x-axis telling us? That's why you have graphs, is because it gives you 2 points and correlates them. Okay, so our x-axis is the mass. Okay, the mass of that particular isotope. Okay, so this particular isotope is zirconium-91, that's its mass number. The y-axis is how abundant or how much of the sample was that substance, right? So we can see right away, the first one you always look for is what is known as the base peak. If you want to label this one, the base peak is the highest one. It's probably the most valuable information because it tells you, of all the isotopes, which one is the most abundant, which gives you the closest idea to like what it is, okay? Then all the other ones are just telling you all the other isotopes that can exist and their abundance as well. So if I were to reach into a bag of zirconium and pull out an atom, what would you bet you're most likely going to pull out? Yeah, most likely this one, right? Like you're winning the lottery if you pull out zirconium-96, okay, because of the chances of getting it. Which, this data is how they generated, or zirconium, this number, right? By doing the math we did last time, that's how it's determined. There's the experimental data, you then do the math to get the weighted average, which matches, right, because it should be closest to 90, right? Now it's not right on 90 because look, all the others are going to pull the average higher, right? So that's why it can't be right at 90 because you don't have any isotopes lower to pull the average that way. Any questions for now on how to interpret these graphs before we try a few problems? Okay, let's take a look at some example problems that you might see on a mass spectrometer, okay? These are somewhat similar to what you'll see on your AP Classroom Quiz 1.2 is all about mass specs, so that's where you'll kind of see questions about that, okay? So this one says, based on the mass spectrum for atom Y, so they're not telling us what it is, they're saying some unknown element, okay, which of the following statements is false? Okay, A says peak A and peak D come from atoms that have the same number of electrons. B says there are 7 isotopes of Y. C says peak C comes from the most abundant isotope of atom Y, and peak D comes from an atom with 4 more protons than the atom that gave peak B. On your own, without looking at your neighbor, I want you to take your best guess of what the answer is. Once again, just be engaged with the process, because I'd rather have you be wrong and try than just wait for an answer. All right, we learn way more from our mistakes than not attempting at all. Set your pencil down when you're not thinking about it and you've circled one. Give you 30 more seconds to make a choice. All right, and then using, like, instead of A, B, C, D, we'll just number them 1, 2, 3, or 4. Show me on your hands what you picked. Okay, a little bit of everything, but that's okay. Nobody's alone in their choices. So let's go through our choices. So A says peak A and D come from atoms that have the same number of electrons. This is not the answer, but it's a tricky one. Anyone know why it's not, Bryson?
Because I mean, it could, but it couldn't, because you can't guarantee the number.
Yeah, it's one of those where you don't know from this graph. This graph gives us no indication about electrons. And so I can't guarantee it's false, I can't guarantee it's true, okay? B, there are 7 isotopes of atom Y. That is for sure true because there are 7 peaks. So that one is definitely true. C says peak C comes from the most abundant isotope of atom Y. That one also is true and we're looking for what's false. So obviously the answer is D, but let's talk about why. So D, peak D, so this one right here comes from an atom with 4 more protons than an atom that gave peak B. Why does that have to be false? Christina?
Because if it's 4 more protons, then it's not actually atom Y anymore.
Yeah, and that's what this is all for atom Y, and protons identify what it is. So very good, thank you. All right, if you pick D, have a smiley face. Any questions on that before we try another one? Okay, try this one, and on this one I'll let you talk to your table.
B.
Okay? I don't know. Okay, you can talk to your table buddy, 2 minutes. Can you identify what the compound is? Ready, set, go.
This one is like, it's like the average of like all of
Yeah, but there is no
That's
Okay, show me same thing. So we'll say 1, 2, 3, or 4. What did you pick? Show me your choice. Be brave.
Oh, wait.
Once again, if you want to say 4 and you look around and no one else is saying 4, but that's what you really think it is, you should show me a 4. Because that tells me as a teacher to explain it more because you didn't quite get it. If everyone has the right answer, then most time we just move on, like right now. Everybody said 2. Good job. Any questions? Molybdenum is the right answer. If you have that, have a smile, please. That's what you were saying.
Yeah.
All right, last one. Try this question. I'll give you 90 seconds. You can talk to your neighbor again if you want. Which peak comes from an atom with the greatest number of neutrons? Ready, set, go.
It's just the amount of
It's not asking like about your abundance, it's like a question about like
I need a getting out work on Friday.
Alright, 5, 4, 3, 2, 1. Show me your answer. What do you think it is? Very good. Any questions on interpreting mass specs? They're pretty straightforward once you know what they're talking about. But it is something that you'll see on our test. It's guaranteed to be on the AP test. So it should be one of those things that really is like, ooh, I'm excited to see this because they should be not too difficult to solve. So, but once again, that's what your homework or your AP Classroom Quiz 1.2. Okay? Just FYI, if it helps you at all, so on your front of your notes, I gave you like a cover sheet of all of our topics. The quizzes and the homework's number match the topic they're about, which is also labeled in the notes. So in case that ever helps you keep track, like if you're like, oh, I did not do very good on quiz 1.2, if you go back to section 1.2 in your notes, that's the same stuff it's covering. So you can kind of help you keep track maybe of where we're lacking as we're learning. Of like, I don't understand this topic very well, I need more help with it. Okay? All right, we're kind of transitioning quite a bit besides it's still chemistry, but it feels quite different from before. Okay, so flip your page over. Now this I want you to do on your own. Okay, there's a reason to this weird question besides I really like donuts. Donuts are probably like my favorite thing ever. But I want you to show or explain how you would determine how many donuts are in 3.5 dozen. So I don't want just an answer. I need some work, I need some words. How would you do this? I have confidence you all know how to do it, but I want to see how you would do it, okay? I'll give you 2 minutes. Show me, I need words and numbers. Explain to me how you get there. Pretend you're the teacher, I'm the student, and I don't know how to do this problem. How would you teach me how to do it? Set your pencil down when you're done writing. That way I know you're not thinking anymore. Okay, turn to your table buddy, and whoever is the oldest this time, you need to teach your table buddy how to do this problem. Ready, set, go.
I just wrote I didn't know
I'm so smart.
like
Yeah, I kind of
more than 250
What is this video?
Okay, give me your attention back up here, everybody. So, there's a reason why I started with that simple analogy, because as simple as that problem was to do, that's how simple, in a sense, the rest of the problems we learned today can be, because it's the same logic. What I really encourage you today is, as we're learning this process, okay, don't get stuck on this side of our chemistry triangle. Students who get stuck here are just focused on the math and the pattern so much, but they don't understand why. Why is that number there? Why am I dividing? Why am I timesing? If you stick here, every problem I give you is going to feel different. If you connect it to here and here, they're all going to feel the same. Because it literally is the same in the big picture. So as we go through that, kind of keep that in mind of like, don't just focus on the pattern, but why am I doing what I'm doing? Okay? So we're going to watch this video, and this will connect to why we started talking about a dozen. Okay? Just like 3 minutes long. It's kind of cheesy, but sometimes cheesy things stick the best. Cheesy things are they? I don't know.
Yeah, duh.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So what's mold now?
So with this idea, okay, so, right, in chemistry, we deal with things that are really, really, really small. Really, 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 really small. And so there's no way that we can actually count them, for one. Just up until maybe 10 or so years ago did we actually build a microscope that can actually see atoms. I say see because like the computer sees it and then gives us a picture. It doesn't actually zoom in for our eyes to see. And it's still quite a fuzzy picture. But there's still ways in which we could group them proportionally, and that's what the mole is, right? So if I have a dozen moles, how many moles do I have? 12, right? So like that number just always equals 12. It doesn't matter what it is. If I have 12 jacks, how many jacks do I have? I mean,
A dozen.
rewind. There we go. I have a dozen jacks, right? Okay, so it doesn't matter what it is, it's always 12. Okay, so a mole is the same way. If I have a mole of jacks, how many jacks do I have? 6.02 times 10 to 23rd. Okay, now that number is on your formula sheets. You don't even have to memorize that number if you ever forget it. It's on the, you turn the page, top right corner, you'll see Avogadro's number. They actually list it as the more accurate 6.22. I've just always learned it as 6.2, so it's just, and what most people talk as, but it does have a few more decimals if you want to be more accurate. Okay, but with this idea, a mole is really only used for chemistry, because outside of chemistry, everything else is too big to count by the mole. As you saw, having a mole of donuts,
That
right,
sounds so yummy though.
like invades the earth, right? It's not practical. But for atoms, a mole is just perfect because now I can hold it in my hand. Where if I tried to hold a dozen atoms, a ream of atoms, even a million atoms, we wouldn't be able to see it. But I can see, this right here is a mole of copper. This one is a mole of aluminum. I'll pass these around so you can hold if you want. Okay, now first off,
Different sizes.
why? Why are they not the same size if they're both a mole, Bryson?
Is it because different atoms that are different sizes? Bigger?
Yeah, right. Just like if I had a dozen elephants and a dozen penguins, they're not going to take up the same space, right? They're not going to have the same mass because the atoms themselves are different. So let me give you another extreme example just to show. So this right here is a mole of water. Give or take what I dropped on the floor. Okay. This is a mole of sugar, sucrose.
Huh.
So explain why such a big difference here. What's going on, Alex?
Well, sugar is kind of like, it's not like based on like weight. This is like how many of each particle. So like sugar is like the whole molecule. So you're counting that many molecules instead of just, well, actually, I guess water is too, but that's a much smaller molecule.
There you go. Yeah, you got to the right place, right? So water is H2O. That's one water molecule, just H2O. But this, right, C12H22O11 is a much bigger molecule. So when you break it down to the smallest it can go, it's just much bigger. Okay? Questions on this idea of what the mole is? Okay? So with this idea of a mole, once again, it's called Avogadro's number. He gets the credit for it. And no matter what, it is always 6.02 times 10 to the 23 of that thing. Okay? We're going to have a phrase that we start today and use the rest of the year. Okay, what we're learning today about the mole is never going away. So don't be like, oh, I'll just ignore this and not learn it. Like everything we do in chemistry goes back to the mole. because the mole is what allows us to see it. If we don't ever get to the mole, then we're just stuck in this world we can't see, right?
So
Yeah.
just connecting it, the mole is the thing that stays constant, but the atom or the molecule is the thing that
The
changes.
substance can change, the mass can change, what we're counting can change, but the mole is the connecting piece. We're gonna start building a map today that will add on to each unit, and the mole is the center of the map. I wish I knew who to give this credit for, but it was quite a few years ago. One of my students came up with the phrase, when in doubt, mole it out. Because the mole is always what we're going to use to get anywhere else, okay? All right, now as we talk about this idea of particles, it's important to recognize like particles can mean many things in chemistry, but it all is the same. We're just counting them. Okay, so particle can be atoms, so an individual atom like atoms of hydrogen. Okay, they could be molecules, which molecules is what you would use for groups of them. So like water, we don't call atoms of water, we call them molecules of water. Okay, formula units, we'll get into more, it's really the same as, or similar to molecules, it's for groups of elements. So with salt, salt is NaCl. We call it a formula unit, but a formula unit is an NaCl hooked together. Once again, similar to molecule. Ions, right, if they're charged or not, and then even like if you wanted to like talk about the electrons in a certain situation. It can be any one of those things, okay? All right, I'm gonna walk you through this first problem together. And what I need you to do, because once again, we're building a foundation of understanding moles that will not leave us, and we need it to be like granite, diamond solid. How that diamond solid is how this foundation needs to be. So I'm going to show you how I need you to set it up. I need you to write it down the same way. If after the Unit 1 test, you can prove to me you've mastered this, and you don't need to write as much information, then that's fine. But until that point, you have to show all your work like I'm showing you, because that's the only way I can help you if it's not going well, okay? Now, I'm going to be using, and I'll do this actually fairly often, I'm going to be using different colored markers on the whiteboard very strategically. It was something I learned in college that really helped me as a student, because I found I had this problem sometimes where I'd go to class, I'd learn a lesson, particularly like in math or chemistry when I was like problem solving, and in class I'd be like, yes, this makes so much sense. Then I'd later go home or go to the library to do my homework, and I was like, oh no. This made sense now, and I'd look at my notes, and I'd still just be like, how did I get from A to Z? And I couldn't see the pathway because it was all there. So I started using different colors to help me see the pathway of my thinking. It was a way to like make it very clear later on. So I put some colored pencils out on your desk if you would like to do that as well, or if you have other different colors. And once again, I'll do this many days of the year. But just to help you kind of, you'll see why, hopefully why the colors are as they are, okay? All right, so the first thing I do when I'm problem solving is I gotta figure out what am I trying to find. So this says how many molecules are in 2.5 moles of that thing. Doesn't matter that you know what that thing is at this point, it's glucose, but that doesn't matter. But I want you all to circle the word molecules. What are you trying to find? Figure that out first. Okay, if we're going on a journey, we gotta know where we're headed, right? It's like, what's that famous Cheshire Cat quote?
That famous what?
What am I talking about from Alice in Wonderland? Like famous quote of like, you don't know where you're going, it doesn't matter what path you take, right? So we gotta know where we're going. Okay, second thing is to identify where are we starting. What do I know? So I'm gonna do that in green here. So I'm gonna underline, this is what I'm starting with. Is red green, is that a colorblind thing?
That is,
Yeah.
Is that any problem for anybody?
That'll probably be a problem.
I just realized that. Blue, red blue, is that better? Is that worse? I don't know. That's not blue markers. Is that blue better? Red blue? Okay, start your path with what you know. Okay, so I'm going to put 2.50, because that's what I know. Now once again with sig figs, that's why I'm keeping that 0, so I remember how many sig figs I have. Okay? Now, in chemistry, all numbers need a unit, so this is 2.5 moles, and a label. So my label is C12, H22, O11. Now for some of you, I know you're going to be dragging your feet like, Miss Elke, so this is so much information to write down to solve this problem. Okay, just trust me in this process, okay? It's worked for students in the past, and it will work for you too if you do the whole thing, okay? All right, so the blue is just what I know, okay? We want to change this into a different unit. Just like with our original question, you were in the unit of a dozen, and you wanted to change it to a unit of a donut. We're doing the same relationship here. So to change our relationship, we need an equivalency that connects the two. So we're going to set up a fraction, because fractions are equivalents to one another. So this is a parentheses, and that's my line for my fraction. Okay, I'm just not closing it because I don't know how far I'm going to write.
Yeah.
Okay? All right, the bottom of the fraction is always the unit you're trying to change. Okay, so I'm going to put moles, C12, H22, O11. Once again, copy, paste the unit, because in a sense, you can think of I want it to cancel, right? Like diagonals cancel away. The top of the fraction should always be the unit you're trying to change it into, as long as there's a direct connection, which whenever it deals with moles, everything connects to moles. So I want to change it into molecules, so I'm going to put that on top. So molecules of C12, H22, O11. The bottom is what I'm leaving, the top is where I'm going. Bryson, did you have a question?
What's this method called again? Like this solving method?
Sometimes it's known as stoichiometry.
Stoichiometry?
Stoichiometry. Okay, now, this right here is independent of the question. This is your true statement of what makes these two things equal. When you're done, you should be able to read this as a sentence because they equal each other. Just like if I were to have a question with feet and inches, okay? If feet are on top and inches are on the bottom, I would say, all right, well, in 1 foot, there are 12 inches. That's what makes them true. So in our case, what makes moles and molecules true? Zachary?
1 and 6.02 times 10 to the 23rd.
Where do they go?
1 mole for every 6.02
Good.
Oh, it's gonna be
Zachary, right? Because 1 mole of something is that many molecules of it every single time, right? Like these numbers have nothing to do with the question, right? They are what make it true. Okay, questions on my setup. Now, we're going to get to a point later today where we may have to take more than one step to get to our answer. But if the top thing is the thing you circled, then you've gotten to your destination and you don't need any more steps. Okay, so now it's just the calculator will do the rest of the heavy lifting for us. So pull out your calculator and let's practice typing these in, because if you're not familiar with typing in scientific notation, we need to. Okay, so pull out your calculator. If you don't have one, you can share with your neighbor, or I can give you one.
Hey! Well, okay, I already have it. That's what best friends are for.
Now, depending on your understanding of math, there are a variety of ways you can type this into your calculator. I'm going to tell you my preferred method, because I guess it's my preferred, but if you type it in a different way and still get the same answer, that's fine. What we don't want is to get the right work but the wrong answer. Okay? So, you always read the problem left to right. Obviously, ignore the units when you're using a calculator. So I'd start by typing in 2.50 into my calculator. Now what I choose to do is, rather than setting up fractions, because that just feels like a lot, I recognize that number ones do nothing mathematically. If you times by 1 or divide by 1, it doesn't do anything. So I just ignore the number ones, and since this is on the top of the fraction, it just needs to multiply by it. So I do this times 6.02, and then I choose to use, there's a shortcut on a lot of calculators for the times 10 button. And I can help you guys find that. And it does an E. If you don't have that shortcut, then you can just type it in fully, like that. So that's the same. If you have a graphing calculator, your shortcut is normally above the comma. So you're gonna hit second comma after you type in the 6.02, and it will type a little E. It's EE on your calculator is what it shows. It's not one E, it's two E's. But when you type it, it will type one. If you can't find it, let me know. If you have a different calculator, you might have it still, or it might just look different. Once again, it's just a shortcut, just saves you some typing.
Oh, okay.
But the nice thing is the E does also like keep it as a group. So if you were like dividing, you wouldn't have to do parentheses, which is nice. If you want to get really fancy and you have a graphing calculator, I can show you how to just save Avogadro's number in your calculator as a variable. That's fun. But
Show us. Ethan, how do you do it?
everyone find it? Everyone type it in, and then let's all see if we can get the same answer, regardless of how you choose to type it in. Okay?
Is it program? Is it program? Variable. Is it a variable?
All right, if you got 1.51 times 10 to the 24, and you typed it in correctly, and you're good. We all get this answer?
Oh, it's because of sig figs. Sig figs.
Did you have a question, Brian? Everyone get this answer? Once again, I don't want you to get it set up right and then always get the wrong answer because the calculator issues. So that's that. Now, this isn't complete. All numbers need
Molecule.
a unit and a label. So now we are in molecules of this. Okay. Questions on how, where, why? That works. Yeah, Gavin.
Wait, did you round to 1.51?
I did, yeah. So because I started with 3 sig figs, that's why I rounded it to 3 sig figs. Yeah, good observation. Any other questions? Side note too, you can report your answer in the shortcut notations. You can do this, E24. That means the same. If you want to write in shortcut. Yeah. Question, Liam?
I did a different way and got 15.05 times 10 to the 23rd, which is the same thing.
That's how your calculator gave it to you?
No, I just did it a different way.
Oh, okay. Yeah, it's the same thing. Technically, the rule for scientific notation is you only ever have one digit to the left of the decimal, but you're correct and you wouldn't get it wrong. So, question? Stretching. Any other questions before I push you into the pool to swim? Okay, try the one right below it with your table buddy for smiley face. Ready, set, go.
I'm just gonna do this after
I don't think we should write this. Really matters. That one number, and then you write that.
Okay, Bryson.
Shut up.
I think it's the same thing, but you just write whatever the answer is, formula units of
So formula units would be the same as
Well, yeah, but you want to keep it the.
I want to know you.
We just set it up the same as the last one.
Yes.
Oh, okay.
I would assume so. Because
It's constant.
it's just how many moles that is a formula.
Okay.
Alright.
Good luck.
Alright, give me a sign.
Doing great. And if you hold it up.
That is 3-1.
converting it out of mold into the actual.
This is pretty simple, but we're gonna.
I got 5.36 times 10 to the 24th.
I didn't ask you.
It'll be 6 a mole is 6.02.
I'm so good.
I'm sorry,
Yeah. How are you? I didn't write anything on my paper.
So the whole times 10 doesn't matter, so it's just, they will just have 3. So you're again gonna have to get 3. Yep.
That's a big one, bro. 5.36 power. 5.36 times 10 to the power 24. I feel like if you said for the rest of your life, they said
Alright, if you got 5.36 times 10 to the 24th formula units, you can have a smiley face. Can you get theirs?
I got 2.
Because they actually can get theirs when they watch this video. They like do the problem. Any questions so far? Okay, so Avogadro's number helps us understand by counting how many atoms are in something. Which, I'll be honest, is like, it's kind of cool to be like, oh wow, there's that many atoms in like this penny. But in terms of like practicality, it's actually kind of like, who really cares? Like, why does that matter? What really matters is our next conversion, because that's what we see, and that's the mass. So our next relationship to the mole, so moles connect to particles. Now we're going to talk about how moles connect to mass. So we have this thing known as the molar mass, which is the mass of 1 mole of an element or compound in the unit of a gram per mole. How many grams per mole is in that substance? Once again, this is what allows us to go into the lab and be like, all right, I need 2 moles for this experiment. I can't count them out because you would die before you count to a mole. You can't count that high, if you could see them even, right? But you can go to a scale and very quickly measure out, and that's how I know that these are all 1 mole is by their mass. So what's really amazing with the mole and how it was, I don't want to say discovered, but developed and made, is the proportion that it has to the periodic table. So on the periodic table, everybody find carbon with me.
I need to get my glasses, bro.
Okay?
I'm struggling right now.
So carbon has an atomic mass of 12.011, at least on this one. Depending on what when you look at, might have more decimals or less. Okay? This number represents the average atomic mass of all the carbon isotopes, right? So on average, a carbon atom is going to weigh about 12 AMUs. It is exactly proportionate to a mole of the substance. So if I want to know how much 1 mole of carbon is, it is 12.01, but now the unit is just a gram per mole. So the periodic table tells you 2 things. It tells you how much a single atom weighs, but in AMUs, and then how much a mole of that substance weighs, but now in grams. So if I want to find the molar mass of aluminum, I just find aluminum on the periodic table, 26. And once again, this is where your answers might vary slightly because depending on what periodic table you look at, the sig fig numbers change. So keep that in mind when you check your answers with mine. They might be, if it's just slightly different, then it's just a difference of a periodic table use. Like I used a different one than you did. Okay, so don't stress about that. Okay, if I'm writing it from the one up on the wall, we'd have this gram per mole.
It says 2 decimal places.
Well, the one I gave you, most of them go to 2, so that's kind of where that was stemming
Oh.
from. I'm just saying, depending on what you look at. But if you were to round mine to 2, then it should match what other one you're using. Okay, before I get to the box of zinc, fill in what it should be for a smiley face. Walking slowly.
Zinc going in 65.38. What was that?
All right, you have 65.38 in that square. Give yourself a smiley face as well. Okay. So sometimes we're dealing with just a pure element. Honestly, most of the time we don't work with pure elements. We work with compounds or molecules when the elements are linked together, aka water, right? H2O. Raise a hand. How would I find the molar mass of water? Because water is not up there. Let's pick. Go ahead, Saraya.
What do you like do because like it's H2O, so you have 2 hydrogen peroxidate, combine that?
Well done. How does mine taste, right? Yeah, you just break down the pieces that it's made of. So if I want to know what is the molar mass of water, well, I go to the periodic table and say, all right, hydrogen has a mass of 1 point, I think on yours it's 008, is that what it's rounded to?
Yeah.
Okay. Now, the little 2, it's called a subscript when they're below, sub, right, small number below. That indicates you have 2 hydrogens, so I'm going to multiply this number by 2. Oxygen has a mass of 16 on your paper, and I only have one of them because the 2 doesn't apply to it. And so I add those all together, and I get an overall mass of 18.02 grams per mole. So that's how much that little cup weighs, or the water inside the cup is 18.02 grams. Questions on that? Okay, we're gonna skip this one, but I want you to practice this one with your table button. So jump down to the bottom one and try that one out in the next 2 minutes. See if you can find its molar mass. Okay?
2 minutes.
Yeah, okay, so
If you use like this, just
I think
yeah, you don't have to.
2 decimal places. So what's magnesium?
Phosphorus.
24 plus 3. Yeah.
So that's like saying.
260. Times 4.
Yeah, Gavin.
Oh. Times 4. Times 2.
Yeah, 260. Per mole. That's a lot of grams. That's
Kilograms actually divided by power.
wait, then what's after gram?
kilogram means 1,000.
Wait, then what's after grams then? No, it's bigger, but like smaller than kilogram. Oh man.
Well, it goes by tens, right? In the metric system.
Customized student system.
It is quite.
I miss Mr.
Oh,
He taught this. He did. This is why I asked for the. Oh,
yeah,
he taught
he taught about the conversion.
conversion. And I forget what he called it. That's why I asked Mrs. Alviza what he called it. Oh.
I was gonna say, this looks close, but something, I knew your final answer was
That was at least I like understood what was before I knew
You said you differentiate for like milligrams, like.
Okay. So with this idea of mass, everybody, give me attention back up here. Okay. So now let's use this idea in relation to conversions. Okay. Once again, try to see the big picture of how it's very similar to what we did before. It just units and numbers change. Okay. So our question says, how many moles of carbon? Is it typed like that on your paper? It's a horrible question. Who wrote this? Okay, you know what? So it should say, how many moles of carbon are in 42.19 grams of carbon? Not potassium. See how it says potassium? We're not to that point yet of like changing elements. We will, but not today. Okay? So we're in carbon and we're staying in carbon. Okay? Yeah, that's just not where we're at. Okay. Alright, so I start with what I know. So the thing that I know is I have 42.19 gram of carbon. Okay, just like before, start with what you know. Oh, so some of you are looking really silly. Okay, I want to change this into what unit?
Mole.
The mole. So the pattern is the same. Whatever unit I'm in should be the unit on the bottom of the fraction. So grams of carbon goes down there. The unit I'm changing into should go on the top. So I want to go to moles of carbon. Now the fraction, once again, is independent of the question. It's always true. So the thing that connects moles and grams is the molar mass. So for every 1 mole of carbon, it's always 12.01 grams. That's always true, because that's how much a mole of carbon weighs. Now, calculator-wise, because this is on the bottom of the fraction now, you're dividing by it.
Andrus to check out?
Yep. So I'd do 42.19 divide 12.01 is how I would choose to type it in rather than typing in a fraction of 1 over 12.01. Questions on my setup or where things came from? So my answer is 3.513.
Yes, ma'am.
What's my label?
Moles.
Sir. Yes, Darren. Okay, questions?
Why would we go to 3 decimal places
So you're thinking the rule for addition and subtraction. The rule for multiplication is since this has 4 digits, I still get 4 digits. But yeah, you're just mixing which I know happens to be. Okay, any other questions so far? Okay, we're gonna play a little game on the practice problem. Okay? Switching roles. I'm your student and you are my 32 teachers. Okay? I do a lot. Okay, now to give everybody a chance to think, okay, I'm going to start walking through this problem. If and when you see me make a mistake, just raise your hand. If you don't think I make mistakes, then just keep your hand down. Okay? But do it like at the point you see it happen. Okay, so our question says, so I wouldn't recommend writing this as I go because I might be making a mistake. Okay. All right, so I'm starting with what I know. So I have 3.10 moles of water. Okay. Oh, you're so supportive.
You're doing great.
All right, so then my teacher told me to put the same unit here. So I'm going to do that there. And And then the unit I'm trying to find is grams, so I'm gonna put that on top. Okay, so then I'm gonna look at the last problem, and last time we used the mass of carbon with grams, so I'm probably gonna use the mass of water, which we found prior was 18.02. I'm gonna put that on here, and then I'll solve. Okay, someone, if you don't mind sharing what I did wrong, keep your hand up. If you don't want to share, you put your hand down. All right, Dylan, please catch me. I thought I did so good.
Isn't it like, it's always, I feel like you said it's always 12.01 for, did you say that? Or did
I don't actually remember what I said.
Okay. Well, yeah, I don't know.
Okay, so something with the mass there. You're on the right track, Dylan. Thanks for sharing out a smiley face. Ephraim, help him out. Add some more to that.
I was just gonna say that you flipped the 1 and the 18.02.
Why?
Because, there would be 18.02 grams inside 1 mole, and you didn't get the right number, I guess. I don't know.
Yeah, right? This is like a lie. I'm saying that 1 gram of water equals 18 moles of water.
Blasphemy.
Like, it doesn't make sense. So if you, once again, make the numbers make sense of what they're representing, the truth is that 1 mole of water is always 18.02. So it should go on. Which in that case, now I'm going to be multiplying, not dividing. So yes, your answer would have been quite different if you did it the other way. But this is where I'm saying, like, make sense of what you're writing down. Don't just try to think, oh, put it on the top, put it on the bottom, and memorize the pattern, because it can flip. But the truth of what the statement is saying never changes. Questions on this one? Okay, our last piece to the puzzle is taking the last 2 things we did and putting it into a 2-step process. So if you come across a question where you're in grams, but you need to get to atoms or particles, it's always going to be 2 steps. Because if you look at that little bridge right there, right here, this one, they're not directly connected. The moles connects them together, so you have to connect it through the mole. It's the only logical way to do it. Okay? So in this problem right here, once again, same pattern, it's going to be a little longer, but it shouldn't feel harder, just longer. So I'm starting in grams, right? So I have 3 grams of copper. What do I want to change grams into? Moles, because when in doubt, go to the mole, right? You always got to go to the mole first. So I'm going to put grams of copper on the bottom, and then mole of copper on top. Now, that's not my end goal, so I'm going to add a second step. Don't do any math yet. Just keep going until you get to your destination. Pattern continues. What unit do I want to change?
Atoms.
Mole of copper. And I want to change it into
Atoms of copper.
atoms. So notice the colors. The reds cancel, the blue cancels. The only thing I'm left with is the thing I want to find. I always build my map, and then I go back for the numbers. It just helps me see the whole picture. So now, look at this independently. What connects grams and moles together? Molar mass every time. Yep, so molar mass of copper is 63.54, 55. So 1 mole is 63.55 grams. Look at the next one as an independent fraction. What connects atoms and moles? There you go, Avogadro's number. That 1 mole is always 6.02 times 10 to the 23rd. And then at that point, now your calculator can do the hard work of the math. Questions on when we start putting it together? And sorry, it was a little rushed here at the end, but. So that's what your homework tonight, the worksheet 1.1 is practicing these conversions. There's some 1-step and then there's some 2-step ones. As always, the answers are posted with work, so you can make sure you're doing it right. If you get stuck or confused, remember you can still come see me on Thursday in Sky Time, and it's not late yet, right? But I recommend you attempt it today so that you know if you need help, you have time to sign up, versus if you wait to do it till Thursday night, then you get stuck, then you run into problems. Yeah, right. Ooh, it's an ugly one, you get one. You get one signature. Because the 3's only, yeah. So that's where it shows you, like, if you don't start with very good data, you don't get to end with very good data. I should have measured my penny more accurately. Okay. I'll be here after school as well, so if you have any questions on this or last time's homework, please come see me, okay?
Yeah, I wasn't paying attention at all. So.
Oh, dang it.